I'm just Mehdi Shah. I'm a postdoc from the Department of Mechanical Engineering under supervision of Dr. Reddy and Dr. Srinivasa. Today, actually, I'm just going to talk about the physics informed modeling interaction for using neural network for autonomous off-road vehicles. And first, as a bit of introduction, I just want to mention that we are just working on there's a project which is nothing but distributed autonomous robotic experiment and simulation, and this project is shared. Yeah, sure. Thank you. And this is a shared project among the two professors, and they are just trying, to build a robot that can, which is able, to slide along a surface, and it must predict what the surface is, and based on the surface, whether it is rigid, clay, or soft soil, natural soil, whatever the case is, to apply appropriate laws to make it able to slide the surface. And for this case, actually, we just need to store the control robotic platform in synchronized augmented reality and real-world environments, and we can see whether it's rigid, we have pure sliding, or whether it is clay or soft soil, slipping and sliding, whatever the case is, happens, and everything, the robots and the tire must predict. And in this way, we need to understand the mechanics of the tire-ground interaction very deeply and in detail. So we just use a finite element analysis, and we have two models, low fidelity and high fidelity models. And for the high fidelity models here, we can see, we can simulate, the actual shape of the tire, but it takes a lot of degrees of freedom elements, and it's very time consuming, and computationally it is very expensive. But very simply, we can simulate the ground and very simple shape of tire, which is in contact on the tire applied moment, and make it a slide over the ground. And for this case, we can use a very simple constituted material models called Drucker-Prager, and we just need to insert the material properties for ground, whatever the case is, again, whether it is rigid, natural source, the soil, or clay, and specifically the stress-strain curves, which vary under various circumstances, and make the model run. But the problem is it's very time consuming for every single case, and the robot doesn't have enough time, to wait for Abacus, the software, to make for every single model and see what is the response. And that's why we are just trying, to neural networks. And for the slipping condition in Abacus, we simply can use the shear stress versus total slip linear relationship when the slope is the K, elastic slip stiffness, and we just actually made our model for various values of K, and we just realized that when we have a very high value for K, for instance, we have 100% sliding for a rigid surface, and at this time distance, we have the maximum value for distance over the time. But when K decreases, for instance, whether the environment is rainy or whatever the case is, we lost friction, some sort of things. That's why the value of K decreases. The simultaneous slipping and sliding happens all the way to 100% slipping when the distance is 0. It means that at that time the tire is just slipping, and at a certain location without sliding along the ground. So this is the mechanics of the ground tire interaction that we just tried, to figure out using finite element method. Another method that we were just trying, to understand what is going on between the tire ground interaction was the using fully empirical model, and the name of this is magic formula. The name is the name magic formula, but it is just for the hard ground, and in this schematic view, we can see the forces, moments applied to the ground, and for various other parameters such as inflation, pressure, the velocity of tire, or whatever the case is, the weight of the tire. We can throw it through magic formula and get the forces, moments, and whatever the case is. And here, one single element shows what the magic formula is, and the y could be force or moments, and x is the slip ratio, the thing that we are just trying to find out. And here we have a few bunch of other parameters such as t, c, p, and they just give the shape of magic formula. And again, we can see the y could be force or moments versus a slip, and those parameters we can build our own big data for various cases, and for the appropriate wide ranges of parameters, and then through it to neural networks and predict the force and moment and whatever the case is. So this is like, as I mentioned, the robot does not have enough time to wait for Abacus to run for every cases to see what the surface is. So first we have to run so many cases for various circumstances, whether it is rigid surface, clay, natural soil, whatever it is, so many things, more than 1,000, and store it in neural networks and provide it for the robot, and make our and speed up our computation using those pre-computed responses. So for the finite element analysis, we have to use the low fidelity models, which is biased and regularization model, but it is inaccurate. But the advantage of using such a model is just to speed up the computation in the least amount of possible time using neural network. But in the meantime, we don't forget the high fidelity model. We just simulate it to learn the errors of the low fidelity model. At least for a couple of and a few cases, we just compare the results and see whether actually that low fidelity model gives a pretty good responses or not, and then distribute the data into neural net and get what we are looking for, such as tire, slip, natural forces, or whatever the case is. And here again, it shows the low fidelity neural nets, and as I mentioned, the advantage of using low fidelity model is neural nets is to just speed up the computation by pre-computing multiple responses, and in this way it makes it the robot able to slide over the ground, and it has a pre-computed responses and or whatever the case is. And this slide again shows that the workflow of the research project for the tire ground interaction that we are using magic formula. It's pretty fully empirical model. We have the Abacus simulation, and then we just create our own big data through it into neural net, and in the meantime we need to compare the results with experiment at least to see for the sake of verification, and then we just make a very good discussion and see what happens at the end of the day. And for the initial results for the magic formula, the analytical methods, that is the single formula that I already showed, to predict the forces versus the slip for various parameters. We just performed a very good parametric study, and we realized that to predict the neural net, we have two types of parameters, which a few of them are insensitive, and we can see their effects are in good shape, and we have no problem to predict a magic formula using neural net because the comparison is pretty good. But a few of them are very sensitive, and for instance, we can see we performed the parametric study on the left here, and they are not in good shape. And using those sensitive parameters, we are not able to predict a magic formula. And I should mention that for insensitive parameters, we just switched off the sensitive parameters, But now we are just trying, to figure out what is going on with this sensitive parameter. Most probably, we just need to, increase the number of training tests and with appropriate range of parameters. And but we are in the middle of it. But I don't see there's a problem. We are just working on it and try our best, to get rid of this issue pretty soon. So as a summary, I just would like to mention again that we are just using finite element analysis, analytical methods to predict and understand the interaction between tire and ground, and various methods will be used to compare the results with experiments. And in this way, we speed up the process and computation by pre-computing multiple responses using neural networks to make the robot able to slide over the ground without any problem. And that's why we call it autonomous off-road vehicles or robots. And thank you for your attention.
Question? So my understanding is that you have generated some data with the finite element method and you have trained the network on that data. So the network itself is data driven, it's not physics informed.
It could be physics informed because when the tire steps on the ground, we just need to know what would be the pressure contribution beneath the tire at various conditions. At various conditions, it just affects the pressure distribution beneath the tire, and then based on that, robot might make decision what would be the appropriate applied force to a step on the ground to make it a slide on the ground. That's why everything just about the physics information that we just know.
So there's a lot of physics, but the physics is used to generate the data using finite element. Then you train the network.
Yes, that's
with that data.
Yes, with that data. Yes.
I understand. Yeah.
Yes. As I understand, it's not applicable only for off-road. It's for all type of vehicles can be used these kind of tools or computers.
Yes, absolutely. But mostly, for the low fidelity models, it's a very explainable model, to try to understand what would be the appropriate interaction between the tire and the ground. But if you just want to use a high fidelity models at that case, you just need to create, the actual shape of the tires. So for every case, that would be different. Thank you.